Hey guys, Dr. B here. This is topic 5.6, reaction energy profile for AP chemistry. The learning objective is to be able to represent the activation of energy and the overall energy change in an elementary reaction using a reaction energy profile. Reaction energy profiles are a way to graphically represent a reaction. The y-axis is potential energy in kilojoules per mole. So I'm going to highlight some of these things. Kilojoules per mole, and the x-axis is reaction coordinate, basically just the progress of the reaction. It shows how the energy of the reaction goes from reactants to products. Remember, we're still talking about collision theory. So for a reaction to occur, your molecules need to collide in a certain way, orientation, with the correct amount of energy. This energy is known as the activation energy, and it's determined by the energy of the transition state, also known as the activated complex. So a lot of terms here that we're just kind of throwing at you. The activation energy for the forward reaction is energy of the transition state minus energy of the reactants. So imagine you can do some math by interpreting a graph with this equation. The activation for the reverse reaction is energy of the transition state minus the energy of the products. This term enthalpy we're going to see later on in the semester. The enthalpy of the reaction is the potential energy difference between the products and the reactants. For now, know that an exothermic reaction releases energy and the endothermic absorbs energy. I might as well just be painting with this highlighter right now. So the enthalpy of a reaction is delta H, and that equals the energy of the products minus the energy of the reactants. An exothermic reaction has products with a lower potential energy than the reactants because energy is being released. An endothermic reaction has products with a higher potential energy than the reactants because you are absorbing energy. Therefore, an exothermic reaction will have a negative enthalpy value, while an endothermic reaction will have a positive enthalpy value. The transition state or activated complex is the intermediate point between two stable compounds. At this point, the bonds are being broken and formed at the same time. This is like where we need to be, so to speak. When they collide with enough energy, activation energy, it can proceed over to the transition state. And if the energy is greater, if the energy of a transition state is greater, the reaction rate will be slower because fewer collisions will have enough energy to pass this hump. If I have a higher transition state, it's going to take more time. The rate will be slower because you don't have enough enough reactants with enough energy to reach that particular hump, so to speak. So remember that your rate law, so we've been using this quite a bit already. Rate equals K times the concentration of A to some number times, if you have a second one, concentration of B to some other number as well. The value of K accounts for all changes in reaction except for changes in concentration. So we're going to be looking at changes in temperature and something called a catalyst later on, and we're going to represent that graphically. We're going to talk about catalyst and catalysis for the 5.11. So for changes in temperature, that's what we're going to focus on right now. The value of K is dependent on something called the Arrhenius equation. We'll look at that briefly. Luckily for us, we don't need to do math with it, but just the important thing we need to know is that changes in temperature are proportional to changes in the kinetic energy of molecules. We're not changing the mechanism of reaction. We are not changing the mechanism of reaction. We are not changing the transition state. Instead, by changing the temperature, we're going to get a different K value because we're going to be accounting for the large a larger proportion of molecules that have enough energy to get over the hump. Wow, sorry, I didn't mean to do that. So you'll notice in changing the temperature, so just looking at this one here, we're changing the temperature. Your energy activation and activation energy is still the same regardless. By changing the temperature, you are changing the number or the proportion of molecules that have enough energy to be there, to be at that particular level at the very least for its reaction to go through. So a colder temperature, a lower temperature, the average energy of the molecules is not going to reach the activation energy. Second, with a slightly higher temperature, but we're not there yet. As we increase the temperature, you can actually see, try it this way. If this is my T temperature, you have a greater proportion of molecules here that are at a higher level compared to the energy activation. Therefore, they're most likely to go. Conversely, adding a catalyst changes the reaction pathway. That's how you can lower the activation energy. A catalyst is some kind of solid, maybe a gas, something that you add to your reaction that's going to lower the activation energy. On the graph below, draw an energy reaction profile. This is kind of easy. But the important thing we need to do, though, is we're going to show the following things: reactants, transition state, and products. So just remember that the general pattern of these is either going to, for the most part, for these simpler ones, are going to either be something like this or something like that. And it depends on where your reactants and your products are. So your reactants are at 20 kilojoules per mole. So that's somewhere over here. Wow, that's really bad drawing. Your transition state is about 80. And your products are at about 50 over here. So my drawing will be something really ugly, apparently. But remember, when you're doing these things, you might want to label. So you can say your reactants are over here. Transition state, products. You notice that they can potentially ask you some questions like, what is the delta H? What is my activation energy? So if I were going to do that, I'm going to make this in green. My delta H is the difference between my products and reactants. So this is my delta H. My energy activation is a difference between the reactants, the transition state and the reactants. And then from there you can actually do the math for that if you need to. So then my delta H would be energy of the products minus energy of the reactants. So this will be 50 minus 20. So this is going to be 30 plus 30 kilojoules per mole. My EA, my activation energy, is going to be energy of the transition state minus energy of the reactants. So this is going to be 80 minus 20, so 60 kilojoules per mole. All right, if you have any questions, please let me know. Thanks.